Good day, good people. Now let us look at angular motion. Right. Angular motion, let's look at the definition of angular motion. The first definition that I've written here, it says is defined as the motion of an object around a fixed axis or pivot. The second one, it is defined as is the change of position of an object on the circular course. That is angular what? Motion. Is the change of an object on an object on the circular course. Changing position from point A to point B onward on the circular course. That's exactly what they are saying there. Now, examples of objects with rotational motion would be your wheels, would be motors, would be pendulums, right? Now, angular motion is implied when we deal with the following aspects: angular displacement, angular velocity, angular acceleration. Let's make sense of the definition and the aspect that we'll be dealing with under your angular motion. We know that when you change position from point A to point B, you will cover a certain displacement. That we know. When we're dealing with motion under your linear, this aspect will cover them. Now, you will cover that displacement by traveling at a certain velocity. That which we did when we were dealing with a linear motion, that's exactly what we will be dealing with here. But here, the motion occurs on the circular course. We said between A and B, you can't be driving from here to Cape Town, driving at 80 kilometers per hour. Along the road, you will either accelerate or deaccelerate and so forth. You will stop, you will go. Now, as you are driving your beautiful car, stopping and going, you are accelerating and deaccelerating. Now, same thing under your angular motion. That's what we will be dealing with. As the motion occurs on the circular course, you will cover certain displacement. That displacement you will travel at a certain velocity. Now, between point A and point B, you will either accelerate or deaccelerate. Now, those are the three aspects that we will be dealing with under our angular motion. The first aspect that we are dealing with, it is angular displacement. Let us look at the definition of angular displacement. Angular displacement is the motion from one position to another on a circular course, right? It's a motion that takes place on the circular course, changing position from point A to point B on the circular course. Angular gives you the picture that motion took place on the circular course, right? Now, angular displacement, it is denoted as theta, and its SI unit, it is radians or degrees, right? Now, let us look at the definition of radians. Radians is the angle formed at the center of a cycle. It is the angle formed at the center of the cycle. This is the angle that we are talking about of the cycle, right? If the radius of the cycle is marked off on the circumference of the cycle, that's exactly what we did. We are having radius here, point A, we are having radius there, point B. Then that angle gets to be formed. That's what the definition of radians means. Now, having said that the symbol, it is theta, and the SI unit, it is radians or degrees, we then need to know how to convert radians into degrees. When we convert radians into degrees, let's say we are having 3,14. This 3,14, it's in the rad form. Now, converting it into degrees, we then have to multiply by 57.3. When we multiply by 57.3, we would have converted this radians into what? Into degrees, of which it gives us what? 180 degrees. Now, when you convert radians into degrees, what do? We multiply by what? By 57.3. Then when we convert degrees into radians, what do? We divide by what? By 57.3. Then we would have converted the degrees into what? Into radians. Now, the SI unit of theta, it's either in radians or in degrees. Right. Now let us look at how to calculate the angular displacement. In calculating the angular displacement, you would remember that from linear motion, we had V equals to S over T. Now in this case, V, it is denoted as what? As funny W called omega, equals to displacement, the fact that motion occurs on the circumference. We said it that the displacement, it is called what? Theta. It is theta over what? Over time. Now from this formula, you can then manipulate and make theta the subject of the formula, of which it will be omega multiplied by T. Then your answer, it is radius. As much as on the linear, it is S equals to VT, then the answer, it is meters or kilometers or centimeters and so forth. Then here the answer would be what? Radius. Right. It's one of the formulas that you can use to calculate your angular displacement. Another one, it is this formula: theta equals to 2 pi n. This is another formula that we will be using to calculate what? Angular displacement. This formula here. It is 2 pi n. Now the 2 pi, already the 2 pi gives you the picture that motion occurs on the circumference, or it occurs on the circular course, because we know that pi, it is 180. In its degrees form, it is 180. Multiplied by 2, it is 360. It occurs on the circular course. Then the n there, it is number of turns or number of revolutions. How many times have you made your turn on that circular course? That is that n for number of turns. Right, number of turns. Then it's one of the formulas that we will be using to calculate what? Angular displacement. 2 pi n. N for number of turns. Right. Now let us look at the second and the third aspect of your angular motion. The second one, it is called angular velocity. From the linear motion, we defined velocity as the rate of change of what? Of the displacement. Is the rate of change of what? Of displacement. But the fact that motion occurs on the circular course, the definition of angular velocity, that is why you will start by indicating where does motion occurs. Angular, then velocity. The angular gives us the picture. Motion occurred on the circular course. It is defined as it is the rate of change of the angular displacement. It is the rate, now, is the rate of change of the angular what? Displacement. That would be the definition of angular velocity. Now, angular velocity is denoted as omega, like I indicated on the first part. It is denoted, the symbol, it is what? It is the funny W, omega. The SI unit of angular velocity, it is rad per second. Remember we said the SI unit of angular displacement, it is radius, rad, isn't it? Rad or degrees, right? Now, the fact that when we calculate the angular velocity, it is angular displacement over time. It is a rad over per second. All right. Now, from the linear motion, it is V meters per second. Rad, it is one the same thing as what? As your meters. But this time it will be rad per second, the fact that motion occurs on the circular course. Right. In calculating it, it is omega equals to theta over time. Then the SI unit, it is rad per second. Please, what's important under your angular motion is to know the SI unit. If you know the SI units, you will not go wrong. You will not go wrong. You will not mix up the given information with something else. Right. The SI unit for angular velocity, it is rad per second. Right. Another formula that we will be using to calculate angular velocity, it is this formula. Omega equals to 2 pi n. This n there, it is now n for rotational frequency. This n, it is the n for rotational frequency. Number of revolutions per second. Now, as we were making those turns on the circular course, we looked at the number of turns. How many times did you turn? But now we are looking at the speed. As you are making those turns, you are making those turns at what speed? Now, rotational frequency. Right. That n, it is for rotational frequency. The SI unit for this n, it is rev per second, or they denote it as r per second. Now, don't mix the two. The omega, it is what? Rad per second. The n for rotational frequency, the speed at which you were turning, it is called the SI unit, it is rev per second, or it is denoted as r per second. Now, never assume the rotational frequency to be your omega. If you are given the rotational frequency, you will use this formula. You will use this formula. You will use this formula. You will use it to convert the rotational frequency into omega. You will use that formula to do. Now, it is not scientific to use one symbol to denote two different things. It is not, but that's what we are given in our books, and it is accepted in our, in the society of engineering. Now, please don't make the mistake. You are having the n for rotational frequency, and you are having the n for number of turns. The n for number of turns, we are using it to calculate the angular displacement. It is 2 pi n. This one we are looking for rad. But for omega, it is 2 pi n. But here, the SI unit, it is what? Rad per second. Why? The n, they are not the same there. Right. That's what we will be doing. That is what I'm emphasizing here as well. Never assume the rotational frequency to be the omega. Instead, when you are given the n for rotational frequency, convert it to omega. How do you convert it? You convert it by using 2 pi n. Please know the SI units like I'm indicating to you. If you know your SI units, you will not go wrong. Now let us look at the third aspect. The third aspect, it is called angular acceleration. Angular acceleration, it is defined as is the rate of change of the angular velocity. We know that from the linear motion, acceleration equals to v2 minus v1 over t. But the fact that motion has occurred on the angular, on the circular course, right, it is called angular acceleration, and the symbol for angular acceleration, it is alpha, right. The symbol for angular acceleration, it is alpha. Then in calculating angular acceleration, it is the same formula of your linear, but the only thing that changes, it is the symbols to indicate that The other motion occurred on the linear and the other motion occurred on the circular course. It will be alpha equals to omega 2. Now omega 2, it is your V2 or your V final, minus omega 1. Your omega 1, it is your V1 or your initial velocity. Divide by time its time, t its t. Then the SI unit of linear, it is meters per second squared. But the fact that motion has occurred on the circular course, it will be rad per second squared. This, it is the SI unit of angular acceleration as indicated there. Right. That's what we are dealing with here, good people. Now let's look at the formulas that we will be working with under angular motion. Now, I'm having three sets of formulas. I'm having the linear motion one. These ones are the linear motion ones, the one that occurs on the straight line. These ones, we know them. We know this formula. S displacement equals to initial velocity. Initial velocity, sometimes it is denoted as U, or in other books it is denoted as V1. Okay, so that it is to indicate that it is your initial velocity, but in our books I think it is denoted as U, hence I'm using U there. Initial velocity plus final velocity over 2 multiplied by time. This, it is the motion that occurred on the linear motion. When you go to the angular motion, under angular motion, we said it that displacement, this side, it is theta. The angular the displacement on the linear, it is S, denoted as S. Under angular motion, it is denoted as theta. Then we are having initial velocity, this side will be having omega 1 plus omega 2. Initial velocity plus final velocity over 2 multiplied by time. Then we are having this one we've already touched on. Linear acceleration equals to V minus U over time. Then this side it will be omega 2 minus omega 1 over time. Then we are having this one as well, the formula. It is V under linear, it is V equals to initial plus acceleration multiplied by time. These formulas, we know them, hence I wrote them this way so that you can see that that which we are dealing with under angular motion, it is not new. The only thing is that it has occurred on the circular course, that's it. But it is the same formulas. Then we are having omega 2 V final equals to omega 1 plus alpha multiplied by time. Acceleration, angular acceleration multiplied by time. Then we are having V final squared. Then this side we are having omega 2 squared. Don't forget that. Many students, they make a mistake here. They will only write omega 2 and forget to square. And yet the formula here, it is what? V squared. Now if you are given, or if you are to use this formula, don't forget to square it. It is omega 2 for final velocity squared. You need to square it. Equals to omega 1 initial velocity squared plus 2 multiply this side, it is 2 multiplied by acceleration displacement. The fact that we are dealing with motion occurred on the circular course, it is 2 multiplied by alpha multiplied by theta. Then this one, we are having displacement, distance equals to ut plus 1 over 2at squared. This side, omega 1 for initial, multiplied by time plus 1 over 2, alpha multiplied by t squared. Right. Then we are having the bridge formulas. These are the bridge formulas. This, it is the link between the linear and the angular motion. Now, the bridge formulas, if I were to give you the picture, let's say you, for instance, when you are looking at the car, When you are looking at the car, or let's make the example as given in our books, we are given a fish here. Ne? You are given a fish. This fish, you caught the fish with the ray, that fishing rod. Ne? You caught a fish there. Right. You caught a fish. But this is what you would realize. You would realize that that rail on your fishing rod, it's on the rotational motion, or rather it's on the circular course. The omega here, you can tell that the omega there will take place because you caught the fish now, you are railing that rail. You are railing it. As you are turning that wheel on that fishing rod, that wheel on your fishing rod, it's on the angular motion. But the fish that you have caught, it's on the linear motion. That means this one will be experiencing linear velocity. The fish will be experiencing the linear velocity, covering a linear displacement from this point to that point. But while on the rail, everything is angular displacement, angular velocity. Now there's a link between linear motion and angular motion with respect to velocity and acceleration. Now that link, it is this formula. We call them the bridge formula. The bridge formula that bridges a linear motion and angular motion. It is that bridge, bridging the two here, bridging the two concepts. Now you will be using these formulas as well to calculate whatever that they want you to calculate. If you are given the linear displacement and they want you to calculate the angular displacement, you can use this formula. That means it will be angular displacement equals to linear displacement over radius. Over what? Half of the diameter, radius. Okay? Now, if you are given the linear acceleration and they want you to calculate the angular acceleration and you are given the diameter, this formula is applicable, including this one. If you are given the linear velocity and they want you to calculate the omega, it is V over R, then you get your rad per second. I mean, we call them the bridge formulas, bridging the two. Then we are having the additional formulas that I want us to look at. Now, I like to associate them with the bridge formula because here as well you are having the concept of linear and angular. Now, if you are given the linear velocity, or rather they want you to calculate the linear velocity, you are given the rotational frequency. The N there, it is the rotational frequency, don't forget, rotational frequency. This N, it is always associated with speed. If you are given this N and they want you to calculate the linear velocity, then it will be pi multiplied by d multiplied by rotational frequency. Or if you are given the linear and they want you to calculate omega, you are given the linear velocity, they want you to calculate the rotational frequency, then you can use that formula. It will be N for rotational frequency equals to V over pi multiplied by D, then you get what? The rotational frequency. Then another one, it is this one as well. It is this one. In calculating the linear displacement, while you are given what? The number of turns. Right. Then you can use this formula. Or you can manipulate this formula and calculate the number of turns if they want you to calculate the number of turns. If you are given what? The linear displacement. Then you can use that formula. Now, these are the formulas that we'll be working with under our angular motion. Now, the formulas of angular motion, good people, they are exactly the same as the formulas of linear motion. The difference, it is the symbols, how we write those the symbols, how we write them. Right, that's where the difference is, but it is the same concept, same formulas. The only thing that has changed is what? The symbols. That's what we will be dealing with. Now let's look at the application, therefore, of these formulas. Let's look at one application, then we'll continue with the rest of the application on the next video. Now let's take out the data, the given information on this application. We are given the effective diameter. Let's take out the data, the given data. We are given the diameter. It is the effective diameter on the tread of a tire of a car is 555 millimeters. Right. In meters, it will be 0.5555. No? In meters. In meters, it is 0.555 meters. Okay. Now, that's what's given. From here, we can then get our radius, of which it is d divided by 2. Okay. That's the only thing given there. Now, question number 1, it says, question A, calculate the distance that a point on the tread of the tire will cover if the tire does 1 revolution. Now we are given the added information that n revolution, we are given 1 revolution. N, we are given n. Okay. For number A, we are given n, it is 1 rev. For revolution. Now they want us to calculate the distance. Now in calculating the distance, we will be using those bridge formulas. In particular, we will be using this formula because they want us to calculate the distance. Now the only thing that we have, it is the diameter and the n. Then we can be able to get what? The distance that they are looking for. Now it will be S equals to pi dn. It is pi multiplied by 0.555 multiplied by 1. Then our answer would be we get our answer is 1,744 meters. Now, if you know your formulas, if given a question like this, you can solve any questions under your angular motion. And secondly, if you know the SI unit, you can tackle any question. Let's look at question number 2 here. They want us to calculate the angular displacement. The angular displacement, we know that it is denoted as theta, of a point on the thread of the tire after 10 revolutions. This is what they want us to calculate, and we are given extra information. We are given n again as 10 revs. They want us to calculate the angular. In calculating the angular, this is the formula that we'll be using. Angular displacement equals to 2 pi n. This is the formula that I've indicated, that it is one of the formulas that we'll be using to calculate the angular displacement. Now, from the given information, this formula suits the given information. That's the formula that we will be using to calculate the angular displacement. It is 2 pi multiplied by 10, because n, it is given as 10. 2 multiplied by pi multiplied by 10. Then we get our answer as 62,832 rad. Don't forget the SI unit of angular displacement. It is what? Rad, because it occurs between what? It is the motion that takes place on the circular course between those two radii. Remember the definition of radians and the definition of angular displacement. Right. We even said it that we need to know how to convert radius into what? Into degrees. That's number 2. That's how we tackle number 2. Let's look at number 3. The angular velocity of a point on the tread of a tire when the car is traveling at 100 kilometers per hour. Now we are given the linear velocity. Linear velocity is given as 100 kilometers per hour. Let's convert it to meters per second. We'll divide by 3.6. Then we will get 100 divided by 3.6. 3.6. I get my answer as 27,778 meters per second. Now they want us to calculate angular velocity. Now the angular velocity of the point. Now they want us to calculate the angular velocity. Now in calculating the angular velocity, we then have to use this formula. Omega equals to 2 pi n. The n there for what? For rotational frequency. The n there, it is for rotational what? Frequency. But do we have this n? No, we don't have it. But can we get this n? Yes, we can get that n. By using what formula? This formula. V equals to pi dn. And make n the subject of the formula. It is V over pi d. Do we have d? Yes, there's d. Now it will be 27,778 divided by pi multiplied by d, 0.555. Then I get my n then. Divide by pi multiplied by 0.555. Right. Now I get my answer as 15,931 rev per second. Don't make a mistake. This, it is what? Rev per second. Or you can denote it as rev per second. You can say 15,931 rev per second. Now they want us to calculate the omega. Then we are now in a position of using that formula and calculating what? Omega. It is omega equals to 2 pi multiplied by what? By 15,931. Then we get our omega multiplied by 2 multiplied by pi. Now we get our answer as it is 2 multiplied by pi multiplied by 15,931. Right. I get my answer as 100,097 rad per second. That's what we get as our omega. Now we manage then to calculate equation number C. Let us now look at equation number D. Let us now look at equation number D. Let's wipe here. Let's look at equation D. Right. Equation D Equation D, they want us to calculate the angular retardation. This is angular acceleration, but this is angular deacceleration. Deacceleration. Retardation simply means reducing or decreasing. Right, retardation simply means that. Reducing, decreasing, and all that. Now here you can tell they want us to calculate angular acceleration. What is it that we are given? If the vehicle is brought to rest with uniform reduction in speed from 100 kilometers per hour during 25 25 seconds. Now, they want us, in short, to calculate the linear acceleration, not angular acceleration. They want us to calculate linear. Right. From 100 during now. In calculating angular, it's angular. They want us to calculate angular. Right. We've already calculated our omega there. We've already calculated it. Now it is alpha equals to omega 2 minus omega 1 divided by what? By time. We are given time it is 25 seconds. Now we have already converted the 100 kilometers per hour into what? Into omega. This is the one. We were given this, we converted it to that. I'm not going to repeat the process because we have already calculated. Now the given speed here, this speed there, it is your initial velocity. Now we are having 0 minus 100,097 divided by 25. Then our answer would be 4, negative 4 rad per second squared. Because the answer it is negative because we are told that we need to calculate the deacceleration, angular deacceleration, retardation. This is how you tackle questions on your angular displacement. When you know your formulas, when you know the SI units, you will not go wrong. This is how we tackle them, good people. Thank you, good people. I will then post the application. I will then thereafter continue to post the application of what? Of angular motion. Thank you, good people.